To thank the organizers for the invitation to be here today. And I was asked to talk about the topic of where does the road of UHF lead us. And I think this is intended to start you thinking about some of these topics for the podium discussion that's going to happen right after this presentation. So here are some data that I got from Franz Schmidt. They're a little bit outdated, but they were showing, that 3 Tesla was really taking over a large segment of the market, but basically by displacing everything below 1.5 Tesla. And it was quite impressive to hear that Siemens has basically doubled the number of customers working with 7 Tesla or to be installed. But if you look at this in relative terms, it's a very minuscule part of the market, so there's lots of room to grow. So that's hopefully one way we can look into the future. And why do people want to work with 7 Tesla? Well, we saw this in particular yesterday and continuing today. We can go to higher resolutions. We get augmented contrasts, including in particular T2 star, which is also the basis for functional MRI. And what I think is extremely important, especially about thinking about even higher fields, is the emergence really of metabolic information and the practicality of getting that information with the enhanced sensitivity, be that through spectroscopic techniques or with X nuclei. So where does the road lead us? And I won't be able to give you comment on a lot of aspects, but I think in general it leads us to more. There's lots more gold out there to be mined in terms of getting information about physiological processes, about brain function, and also studying just healthy human physiology. But one of the first things that I think we're going to see happen in the future is given by this data, which shows basically the distribution of cancer in different organs of the body. And if you look at this, and you look at the prominence of prevalence of brain cancer, it's very minimal compared to the rest of the body. So I think the real thing that has to be done is to expand the application of 7 Tesla to other regions of the body beyond the small joints and head. And we saw in the PTX session, a lot of this groundwork has already been done. The tools are out there. But it needs to be translated into a very reliable, consistent, fast workflow to do this. So I won't say exactly which coil out there is the best. There are many different examples, and I think that if you do use these techniques, you can show that, especially as Harald Quick showed in his talk, you can get very good image quality in any region of the body. So for me, this what does fully clinical 7 Tesla mean? It means we should be able to examine any organ in any body shape, and it has to work basically every time. So similar to what you expect from lower field strengths. Another aspect of more is obvious, I think, is going to higher magnetic field strengths, as Camille just presented. 10.5 Tesla. There are also magnets that will be coming online or coming back online at 11.7 Tesla. These developments are going to be extremely exciting for all of us in the field. And this diagram I took from a paper by Tom Bunninger and colleagues, and what they were looking at was basically the maximum field strength that has been achieved versus the warm bore size of the magnet. And so at the lower end you have small animal systems which go all the way up to 21 Tesla, and in the human-sized magnets you have until recently 9.4 Tesla, but as we've seen now these other systems coming online. And what is interesting is that there is sort of a natural barrier here provided by the superconducting technology of niobium titanium. If you want to cross this barrier then to a higher field strength, it looks like we're going to have to change to niobium-10. And there are actually several projects now looking at doing this, and as far as I know, most of them are looking at going to 14 Tesla, either in a head size magnet or even in a whole body magnet. For instance, there's plans for a German national imaging facility which is looking at a whole body system, similar plans in the Netherlands, and also projects in China, the USA going on. So what can we expect by going to these really high field strengths? And the conventional wisdom is that signal-to-noise ratio goes up linearly, at least if you're in the sample-dominated noise region. But if you look at the experimental work that's been done as well as simulations, then you find that signal-to-noise ratio should actually go up faster than linearly. And this is not because we're falling back into the coil-dominated noise region. We're actually going into a different electromagnetic regime. It's the same effects that cause non-uniformity in our images, give us this additional benefit in signal-to-noise ratio. And for the further discussion, I will assume basically this factor of 1.65, which was in the paper of Pullman et al. So that if you use this, then you would expect a factor of 3 in SNR increase at 14 Tesla. So what could you do with this? I mean, these are some data that were given to me by Oliver Speck from Magdeburg, showing some of the highest resolution whole brain images acquired with 250 micron resolution. And they show really astounding detail. They spend a lot of effort compensating for motion, etc. But they also spent quite a bit of time in acquiring these data. So at 14 Tesla, what if you could acquire these data in just 3 minutes? It would open up, completely new possibilities for high-resolution structural imaging. But I think the real potential of ultra-high field may be not really in the conventional imaging with water and fat, but may actually lie in some of the alternative techniques where we look at other metabolites as well as other nuclei. And just to motivate that, I want to talk about the Warburg effect, which was presented yesterday, which is quite well known, that cancer cells, for some reason, change to an alternate form of metabolism that is not dependent on oxygen, but it is also very inefficient. It produces much fewer ATP than the equivalent normal oxidative metabolism. And this is sort of the basis then for FDG PET, because the cancer cells need a lot of glucose to get enough energy to live and grow. But we can now look at this glucose also with magnetic resonance techniques based on CEST-like techniques. And you can see quite clearly the high glucose uptake in the border of this glioblastoma. And Moritz Seiss presented quite a bit on CEST yesterday, but I wanted to pick up on one point, which is that if you look at this in vivo Z-spectrum, which was collected at 7 Tesla, so I think it was like 70 different points in the spectrum acquired, 70 different images. If you look at what makes it up, it's actually quite complex. There are many different components, metabolites, proteins, lipids, going into forming the spectrum. And if we have the additional field strength, then we should be able to have improved sensitivity and hopefully also selectivity in order to really improve the application of these techniques, for instance, in cancer or osteoarthritis, or for looking at neurotransmitters. And another way of looking at the Warburg effect can be done by using oxygen, in this case oxygen 17, because oxygen 16 is not MR active. And you don't have very much oxygen 17 in your body, but you can inhale enriched gas. And in this case, the nice thing is that the oxygen 17 is not visible with MR imaging until it gets to the cells and is metabolized into water. So when it's flowing through the blood, it's not visible. And so therefore, you can do very quantitative measurements of metabolism. And in this case, you can see the spatial resolution was about 7.5 millimeters. And at 14 Tesla, then we could get down to, say, under 5 millimeter resolution, which is on the level of the thickness of the cortex. So I would expect that we would have additional possibilities with that as well. And just a last example from phosphorus imaging. Phosphorus imaging, Tom Skeenan talked about this extensively yesterday for energy metabolism, but another nice aspect is you can monitor pH with this, and it's fairly straightforward to monitor the intracellular pH, which is shown here. But you can, at 7 Tesla now, start to pick up two distinct peaks in the inorganic phosphate, which can be attributed to the intracellular and extracellular compartments. And what we see is that we can do this in some of the voxels, but it's not completely reliable. There are some voxels where we can't really separate out the peaks. So if we go to even higher field strength, then we would expect that this becomes easier and more reliable to do, maybe even in individual patients. So what are the challenges that we're going to face if we want to go to higher magnetic fields? And there are probably many, but one is certainly the uniformity problems get more difficult. So now parallel transmission becomes key not only in the body, but also in the brain, and as well in the for other nuclei beyond just hydrogen. And the nice thing is that actually much of this work has already been done. We faced these challenges at 7 Tesla, and they haven't made it into routine clinical use yet. That's still being processed, but in a research environment, we can do this. And I think Camille mentioned one time that he was kind of disappointed in the first images at 10.5 Tesla, which thank you that you did those in the prostate, because they were so good. And it looks like this is going to be a little bit easier than expected. So technically, probably the biggest challenge is the magnet itself. And we, as part of the German consortium, have been talking to various magnet manufacturers. And if you talk to them, basically they say it's a challenge and it's going to cost a significant amount of money, but it's technically feasible. And what's also nice is because you are changing the superconductor, the price of the system will not scale directly with the material costs because you need less superconducting material because you can run the magnet at higher currents. And also the size of the magnet doesn't scale as you might expect. So these will not be huge monsters. Depending on how aggressive you make the design, they can actually become fairly compact. So one of the additional challenges related to that, which I didn't show here explicitly, is that you may need to have some new organizational forms in order to finance and operate these systems. For instance, in both Germany and the Netherlands, these are going to be operated as national facilities and provide open access to the users, sort of like CERN does for particle physics. So where do I see the real challenge or the limiting factor and how high we go? I think this will be determined by human physiology. There are concerns about blood pressure increases. We already see changes in the EKG at 7 Tesla, but so far no significant changes in blood pressure or heart rate. There have also been some reports of cognitive effects related to the static magnetic field, but also other reports showing no correlation. So if we are in that vicinity, it's still not really significant. So it's something that definitely has to be followed up, as is being done at 10.5 Tesla. And there were some reports a few years ago of DNA damage resulting from MR examinations. Wasn't really targeted at the static magnetic field per se, but now there's been quite a bit of data collected, for instance, in Magdeburg, showing that there is no reason for concern due to the high static magnetic fields. So where do we see or I see the ultimate limit, or actually see effects? We see that in the vestibular system. There are things like vertigo, metallic taste, nausea that can happen at 7 Tesla, but these aren't yet too significant, and there's some, advice to move volunteers and patients slowly into the magnet. However, I would like to point out that even if you're stationary in the magnetic field, you will be able to observe things like nystagmus, and this has been attributed to flow of the endolymph in your inner ear, which interacts with the static magnetic field, and therefore causes your eyes to continually try to follow some sort of imaginary motion. And you can see that this can be observed also in animals. These are rat experiments done at 14 Tesla of exposure. And one magnet was done head up in the magnet, and the other one was done head down. And they will tend to circle like this for about 3 minutes after the exposure. And I think it would be quite interesting if you try to ask your patients before they go into the magnet, would you prefer to turn left or right going home today? But what's interesting is that they also point out that the orientation of the human head to the magnetic field is actually almost optimal compared to the rats. The rats were put in the worst case orientation that you can have. So if you really want to avoid these magnetic vestibular effects, you should worry about the tilt of the head of your subjects more perhaps even than the motion through the magnetic field. But at some point it could become an issue. So where do I see the future? Full body clinical 7 Tesla is hopefully on the horizon. These projects with 10.5 and 11.7 Tesla are extremely significant steps, but I'm hoping that they will not be the end in the journey. And I think there's a lot more that can be discovered with these high field systems. If you think about going to spatial resolutions on the order of 100 microns, or voxel sizes for fMRI below 0.5 millimeters, and having access to metabolic information from X nuclei. And I don't want to venture a guess on where the ultimate human physiological limit might be, because we don't have enough data to answer that yet. But I am assuming that at some point these effects will become significant enough that we will have to start worrying about them. With that, I'd like to conclude, and thank you for attention.
Right, since Mark is not part of the panel discussion, does anybody have a question that they want to ask Mark? Yes, there's a question at the front there from Camille.
The 14 Tesla safety data you got with the rats, were they done in a chemistry magnet, or with the head like this and vertical?
Yeah, they were done in a vertical bore magnet,
so
sort of
that's why
State
you had
University.
the head up or down.
Yeah, and so you could do that up or down. And because of the anatomy of the rats, the orientation of the horizontal semicircular canal is basically in the worst case position. And if they position the rats with 90-degree orientation, which I don't know exactly how they do that because of the limitation on the bore size, but they said that they don't see these circulating effects at all.
Interesting.
One quick question from me, Mark. In terms of RF coil design, have your simulations suggested that we're going to need a step change in how we go about designing coils at 14 Tesla, or do you think we can apply the sorts of coil designs that have been developed for high field so far?
Well, we have currently simulations going on related to that, and it's too preliminary to say anything right now, but I would say that I don't see a dramatic change. I think Camille has shown very well that at 10.5 Tesla you can extend what has been done at 7 Tesla, and basically more than a magnetic or an electric antenna, basically subcomponent there isn't out there, so it has to be something in that direction.
Okay, thank you.